Good morning, and welcome to today's Oil and Gas Journal webinar, How to Improve Accuracy and Safety in High Viscosity Sampling, sponsored by Swagelock. I am Chris Smith, Editor-in-Chief of Oil and Gas Journal with Endeavor Business Media. To begin, let me explain how you can participate in today's presentation. First, if you have any technical difficulties during today's session, please submit them to the questions window, and our technical experts will help you out. We recommend disabling any pop-up blocking software or extensions in your browser, as these can cause issues with the webinar player. Additionally, we welcome your questions during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. To do so, simply type your question into the question window on the side of your screen and hit the submit button. Also, please be aware that today's session is being recorded and will be available on the Oil and Gas Journal website within the next 24 hours. You'll be notified by email when the archive is available. Now, I would like to introduce our speaker for today's discussion. Matt Dixon is the Application Commercialization Manager at Swagelock. Over the first 6 years of his Swagelock career, he worked as an assembly, welding, and manufacturing engineer, supporting the production of high-volume fittings and various hose product lines, designing and building assembly and test equipment. In 2004, Matt joined the Custom Solutions team at Swagelock. His past hands-on experience with Swagelock products has enabled him to grow in this role into a leading integration and applications expert within the Swagelock organization. Welcome, Matt. Please go ahead.
All right. Thank you very much. Let's go ahead and jump right into the content. So just to make sure that we're all level set on what we're talking about, let's define what grab sampling actually is. So grab sampling is all about taking a sample out of the pipeline or tank or system and then transporting it to a remote laboratory for analysis. It's known by a lot of different names: sampler, spot sampler, lab sampler, field sampler. Here at Swagelock, and a lot of industry just calls it grab sampling. There are a lot of different types of samplers out there. Cylinder samplers, bottle samplers. Today we're going to be talking about viscous sampling, which is typically going to be bottle sampling, but we'll kind of talk a little bit about both, but we'll focus primarily on the viscous sampling stuff. All right. So with sampling, why are we actually doing grab sampling? There's a lot of different reasons. So we need to validate that the process is producing whatever it's supposed to be producing, whether that's interstage, between units within the facility, or it could be the final product, as it either leaves the facility or where it is going into storage. So anytime that you have any sort of a change of custody. So for example, if you have crude oil coming into a facility, maybe being transferred from a tanker into an onshore facility, there's going to be some sort of a sampling operation that goes on there anytime there's a change of custody like that. Environmental situations. Of course, we need to make sure that we know what's being released to the environment, whether we are doing so directly in our facility, or maybe it's something that's going to be contained in our products. For example, mercury and gasoline. That's the type of thing that we need to monitor. And then also validation of online analyzers. Within a facility, grab sampling is one way of sampling. Another way is to actually have an online analyzer that is giving a live, real-time result in terms of what is flowing through that pipeline. So in that scenario, we very often have a grab sampling system associated with that online analyzer to periodically validate those results to make sure that those results are reading true. So when we're looking at sampling, one of the basic considerations is, what sort of sample container am I going to use? So, there are a lot of different considerations that go into this. One of those is toxicity. From a toxicity standpoint, you really need to have a sample container that is going to very effectively contain that sample so that you minimize exposure to the operator and to the environment. So in that scenario, a sample cylinder might be the best option. Not so much typically in a viscous sample, because the sample cylinder is generally not very effective at enabling you to collect that viscous sample. And most times in a viscous sample, we're going to be using a bottle of some sort. And that is actually driven by one, just the application, but two, the economics of it as well. A bottle is certainly going to be more cost effective than a sample cylinder, a lot less expensive. So for that situation, it, a bottle is really the choice for a liquid, unless the toxicity or something else like the sample volatility really drives us to use a sample cylinder. Now, with a viscous sample, we generally don't have to worry about the volatility. So really, toxicity is the only thing that might even give us pause to think about some additional containment beyond just a simple sample bottle. Now, when we're talking about viscous samples, we're looking at an example here that is the core product, or sorry, the core process in a refinery, right? We've got a distillation tower. The bottom left, you've got the crude oil coming in, it's being boiled. And you've got different levels of the tower, different, those hot vapors are condensing. We've got different products recondensing as they come out of the tower. And each one of those points, you're going to have grab sampling operations. Now, those things way up at the top of the tower that are coming out that are maybe not even recondensing, those are going to be your really light gases, your methanes, your ethanes, things of that nature. In the middle, you've got your volatile liquids. So some of those liquids that under pressure, they're going to be liquids, but if you release the pressure, then they could potentially vaporize into a gas. The things we're mostly concerned about today are those liquids down there at the bottom. Even beyond some of the fuel oils and things like that, even down even lower, we're looking at things like the bitumens that could potentially be coming out of our tower. Well, not potentially, they will be coming out of our tower, and we're going to need to be able to sample those. So that's primarily what we're talking about today. But when we're looking at this operation, there are a lot of different considerations. So for those things up at the top, we're probably going to want to use a sample cylinder because, again, those are gases or volatile liquids. For the things down at the bottom, again, we're going to probably use some sort of a sample bottle. Now, when we're looking at this example with the distillation tower and the different hydrocarbons that may be coming out of this, let's look at a couple of them. Pentane, for example. Pentane, we can see that it's got a boiling point of 36C. 36C, that's not excessively warm, even here where I'm located in Cleveland, Ohio. It does occasionally get up to 36C, not in February, of course, but it does occasionally get up. So for pentane, we would consider that to be a volatile liquid. Now compare that to the one below it, hexane, got a 69C. Hopefully there's nowhere in the world that gets up to 69C, so we would generally consider that to be a non-volatile liquid. So that's about where we would draw that line. Anything above that hexane pentane line, we would really consider using a sample cylinder. Probably that's going to be the best choice. Down below that, and including our viscous liquids, we're going to be using a sample cylinder, a sample bottle, unless other conditions such as toxicity drive us to use something else. So let's look at one example of some of the fluids coming out of this tower, and we'll look at the bottom one. We'll look at bitumen. Now, bitumen is, if you're not familiar with it, this is basically what we often referred to as the bottoms of the tower. This is the heaviest component of the crude oil coming in. Never actually boils. It doesn't actually vaporize. So it's coming out. It's really heavy. What it's used for primarily is for asphalt. You mix it with aggregates, stones and sand, and that is what we pave our roads with, of course. Very similar to tar. Tar is a little bit different. Actually, tar is a little bit thinner. Tar is derived more from coal or wood, whereas bitumen, again, is derived from oil. Now, when we're looking at bitumen and other viscous fluids, we need to understand that there is a relationship between the viscosity of that fluid and the temperature. So we've got it's got a scale down there at the bottom of the slide showing different fluids, different viscosities. The far left end, we've got air. Kind of in the middle there, we've got water. It is 1 centipoise. However, at the far end, we've got molasses at 20,000. So if you've seen molasses and how it flows, and of course, there's the phrase "slow as molasses," and that's how it gets its name. It's just it's a viscous liquid. It doesn't flow very well. Not everybody's seen molasses, so close to that on that end of the scale is honey. I think most people have seen honey and how it flows. So understanding though, where, how a sample, how that temperature impacts a sample will help us to understand how we need to treat that sample when we're sampling it. So let's looking at bitumen, for example. If we keep that up at 300 C, our viscosity is down at 2 or 3 centipoise. So we're pretty darn close to water. So it's flowing very, very well at that point. All right, but let's suppose we let the temperature drop to 200 C. All right, so now we're up to about 10 centipoise. We're getting into some of the range of some of the oils. All right, if we drop it down to 100 C, boy, now we've really jumped quite a bit. We're maybe a couple hundred centipoise. So we've exceeded olive oil. We're approaching motor oil. Go a little bit lower to 80 degrees C. 80 degrees C, and now we are up at about 1,000 centipoise. So we're starting to really get up there. It's really starting to flow. And here we go. Here's at about 50 degrees C. So now we're just starting to get into ambient temperature. So 50 degrees C, 120 degrees Fahrenheit. This is hot ambient temperature, and you can see that we are now approaching that honey range, right? We are getting pretty darn viscous at this point. One more I'll show you here. So 20 degrees, and you can see we're well off the scale off to the right. We're into the hundreds of thousands of centipoise, and this is what you would call a plug. And that's one of the lessons that you have with viscous samples is you don't want to cool them to the point where they slow down and actually plug your system. That's something that's very easy to do. So a few general tips for sampling viscous liquids. We want to make sure that we're keeping that liquid at least 20 degrees C above its pour point. That's something that we need to make sure we're doing so that it doesn't slow down and again plug. Now, we have to balance that against safe handling of liquids. Now, if you're the ideal situation is that you would cool that sample down to at a maximum of 60 degrees C to avoid burns for the individual who's collecting that sample. That may not always be possible. If you go back to our bitumen example, if you cool it down to 60 C, that's going to be really challenging to sample that liquid at that temperature. We're also going to want to have some sort of purge very often in order to get that sample out of our sampling system after we take the sample, get any residues out. Nitrogen is used sometimes, solvent, very common to use steam to purge out your sampling system afterwards. You can use coolers if you want to cool down the sample coming in. That is, that's something that's pretty frequently done. And again, we're not cooling down to ambient temperatures. Very often, we're not cooling down to safe handling temperatures, but instead, we're cooling down just to take the edge off, so to speak, of the temperature. And of course, when we're doing this, we're sampling a liquid. It could potentially splatter. Got a hot liquid. We want to make sure that operator is well protected. So very often, you're going to have this in some sort of a enclosure or something like that to make sure that the operator is not exposed to any splatters or anything like that. Okay, so when we're looking at sampling a viscous liquid or liquids in general, there are a number of different options that we can potentially have. Metal can is probably the most common for viscous liquids, especially on in a refinery when we're sampling that bitumen or something at that low end, the bottoms coming out of the tower. Very often a 1 quart paint can, like what you see there, or the tall rectangular kind, I believe that's called an F style can. Those are very commonly used for sampling those viscous liquids. Another possibility, depending on the fluid that you're sampling, is a glass bottle. We've got Boston round bottles and media bottles. Now with these, we've got to make sure that, much like the metal cans, we're not worried about toxicity, because if we're dealing with an open top container, the operator is going to be exposed to whatever vapors are coming off of that fluid. So we got to make sure that if we're sampling using a metal can or a glass bottle, that it's a non-toxic sample and that don't have to worry about exposure to the operator. Now, in a lot of different sampling operations, you'll see septa that are applied to the top of the bottle, and then that's pierced with some needles to dispense a sample. Now, with a viscous liquid, you're typically not going to see that for two reasons. One, if trying to push that viscous liquid through some small diameter needles, it's very difficult to do, of course. And if you heat it up to the point where it can pass through those through those small diameter needles, chances are you're going to meet or exceed the temperature limitations of the cap and septum itself. So generally, we're looking at either the cans or the glass bottles. So let's take a look at some of the pros and cons of those. So for a glass bottle, one of the pros, of course, is they're very commonly available. You can get those at just about any laboratory supply company. Two main styles that you're going to see out there are Boston Round, which is more prevalent here in North America, and then media bottles, which are prevalent pretty much everywhere else. There are other styles, of course, but those are the two main ones. One great advantage of these is that you can actually see the liquid level, as opposed to with a metal can, much more difficult to do. Again, you can get them with a septum, probably not for this application, but you can get those with a septum. They are pretty much universally compatible with anything that you're going to be sampling. It's not going to contaminate your sample. You don't have to worry about corrosion. The one exception to that I'm aware of is HF acid, which is not compatible with borosilicate glass. But if you're trying to sample HF acid with a glass bottle, that is very not advisable, just due to the extreme toxicity of the HF acid. And of course, it's very easy to open or close. You can get those with twist top bottles. Very easy to do. Now, of course, there are some drawbacks. The number one being temperature. So you've got the temperature limitations. The bottle itself, the glass itself, can take temperatures up to 260 C or about 500 F, which with bitumen, that's probably about where you're going to be sampling it. It might come out of the tower a little bit hotter than that, but you're probably going to cool that down a bit to actually take the sample. So in the 400 to 500 degree Fahrenheit range is probably where you're going to be taking that sample. But the issue is that you have to worry about the thermal shock. When you're putting that hot sample into a bottle that is at ambient temperature, you can cause a extreme temperature gradient through that glass, which will cause it to crack and shatter. So you have that thermal shock rating of the glass, which is about 160 C or 290 F. So as a result, if you're taking a sample of something that's really hot, you're probably not going to be using a glass bottle. Chances are you're going to be using a metal can. Again, pretty readily available, generally in steel. They are pretty inexpensive. You can get them just about anywhere, even at Home Depot if you wanted to. Because they're metal, they can handle the high temperatures. There are some considerations about compatibility. Generally, they're plated steel or have an epoxy liner. Like what you see there is an epoxy liner, that dull gray liner. So there is some consideration about about compatibility. Generally, that's pretty compatible with with some of the applications you're going to find in refineries and chemical plants. But just something to double check. Another consideration, another drawback is that you do need tools to open and close them, whether it's a hammer to close or a screwdriver or tool, a prying tool to open that back up. Another consideration is that you can't see the liquid level very easily when you're filling it. If you can look down into the top, of course you can see it, but it's something that's it can be a challenge sometimes, especially if you're trying to look through a dirty window in an enclosure to look down into that bottle to see if you filled it appropriately. One strategy I've seen some customers take is actually to use a thermal label. And of course, we've all seen thermal paper. We've seen it with a receipt. Here's an example of a receipt that was actually put onto a stove. This is an example of what happens when you expose that thermal paper to heat. So you can actually use this self-adhesive, put it onto the side of the metal can, and then as the as the liquid level fills, it'll actually turn black, and you can see the liquid level rising on that label. As long as you don't exceed the auto ignition temperature of that label, you're good, and it's a pretty effective way of actually seeing the liquid level there. All right, so when we're taking a sample, there are a number of basic rules that we want to make sure that we adhere to. We want to make sure that the sample is representative. So that means that whatever sample we extract and capture in our sample container, that actually matches whatever it is that's flowing through our pipe or what that's in our tank. We want to avoid phase changes. Generally not a problem with viscous liquids. We generally don't have to worry too much about those change in phases on us. Well, with the exception of solidifying. Normally, when we're talking about changing phases, we're worried about changing from a gas to a liquid or vice versa. We don't have to worry about that, of course, but we do potentially have to worry about solids and plugging. We also want to make sure that we have a timely sample. So how long does it take to get from the sample tap to our sample container? It's not as important as with online analyzers to get it there super, super quick, but we do need to understand how long it takes. Is it taking us 1 minute to get it there? Is it taking us 10 minutes? Is it taking us 10 hours? We've seen sampling systems that are poorly designed that could potentially take hours and hours, if not longer, to get a sample transported from the sample tap to the sample container. And then also purity. We want to make sure that we're not contaminating that sample in any way along, either by the design of the sample system or by failing to clean out our sample container. They're, including dead legs in our system. So dead legs are something that we always want to consider. So what are dead legs exactly? Dead leg is a branch of a system that doesn't have any flow. And when that happens, you have molecules that fill up that dead leg and actually contaminate our sample as we go along. So let's take a look at an example. Now, this one happens to be a sample cylinder. Again, probably not using a sample cylinder for a viscous sample, but the concept is the same. So suppose we're flowing our sample through our sample cylinder and then back out. And we've got a bypass valve on the inlet side so that when we close that sample cylinder and remove it, we can bypass the flow. And maybe we've got a pressure gauge as well so that we can know the pressure going through that system. All right, so first thing is that we can see here that at some point, these areas filled up with liquid. And we don't know when, we don't know how old that is, but what we do know is that as the liquid flows past the sample inlet, from the sample inlet to the return, all of the, some of the molecules that are in that bypass line or in that gauge are slowly diffusing in and out of that branch and contaminating our sample. So depending on what we're analyzing, that could have a significant impact on on our analysis results. So how do we deal with this? First strategy is to eliminate the dead legs if we can. So for example, with our bypass valve, we could actually change that to a three-way valve. Now we've got a swept flow path, and we don't have to worry about any dead legs or anything like that. And if we can't eliminate it, so for example, with that pressure, maybe we have to know the pressure in the system. Well, let's move that. Let's move that downstream of our sample container. So if we move that gauge downstream, now, yes, we're still going to have molecules diffusing in and out of that branch, but they're being carried away from our sample container, being carried away from the sample cylinder. So they're not influencing our sample. So that's one way that we can deal with dead legs. Another thing that we worry about is, again, the representativeness of the sample. And one way to help with that is to use probes. Now, probes can be challenging, especially with a viscous liquid. But generally, the idea with a probe is that you want to sample from the middle third of the pipeline. And the idea is that that's going to be where you have the most flow. That's where you're going to have the most representative sample that you can extract from that. Now, there are a couple different options. You have a fixed probe, which you see there on the right, which is typically a welded quill that gets mounted to a flanged interface, gets stuck in through a pipe nozzle. Now, it's with that, it's typically made of robust pipe. Might be what we would use for a viscous liquid. On the left there, you actually see a retractable probe. Now that enables us to retract the probe for maintenance, and then that would enable us to maybe send a pig through the pipeline on a periodic basis to clean things out. So they're nice in systems, but in a viscous liquid, they might not be very practical because they actually are made out of typically tubing, smaller diameter tubing. They're probably just not going to be able to withstand the flow of viscous liquid that's going perpendicular to their axis. So if you're going to use a probe in a viscous application, you're probably going to be using a pretty robust pipe probe, and make sure that it's good enough to withstand that viscous flow. All right, so when we're tapping our system, where are we actually going to take the sample from? So if we're looking at process piping, like you see there at the top right of the screen, you can see we've got a few different options. We've got some horizontal pipes, we've got some vertical pipes. Where are we actually going to be sampling from? Horizontal pipes are pretty good to sample a liquid from. A vertical, upward flowing pipe is also another option. We're pretty sure that that's going to be full of liquid just because of the way the flow is. However, what we probably want to avoid are the downflowing vertical pipes in a liquid application, because you can have what's called the waterfall effect. It's essentially a waterfall within that pipe. And then when you're taking the sample, you could get a mix of vapor and liquid. So in that scenario, we're going to want to avoid that vertical downflowing pipe. Now, if we look at the cross section of a pipe, where do we want to take the sample from? We've got a number of different options, of course. We could put the sample taps at the top, the bottom, or the sides. What's going to be the best for us? Well, as you're looking at that cross-sectional view of the pipe, you can see that there could actually be some vapor at the top of the pipe. So we need to take that into consideration. So let's suppose we have a probe. We're taking our sample through a probe. In that scenario, we're reaching into that middle third of the pipe. So even if we're going from the top or the bottom, we're reaching into the middle third, and we're really not going to be affected by that vapor. So we can probably take a sample out of any one. But of course, if we put a sample nozzle on the bottom of the pipe, that's going to be a great place to collect sediments, especially in something like the bottoms out of the distillation tower, where you're going to have solids. You're going to end up with a lot of sludge down in that. So probably not the best idea to put it on the bottom. So ideally the sides is going to be the best situation. You could do it at the bottom if you had to. Now let's talk about a scenario where we don't have probes. Now remember, we still have all that sediment down there at the bottom, so we probably want to avoid taking that sample down there from the bottom, because again, we're going to get tons of solids and contamination into our sampling system. And remember, we have that vapor up at the top potentially in that horizontal pipe. So we want to avoid taking from the sample from the top as well, because you're going to get a mix potentially of vapor and liquid. So if you're not using a probe, then definitely you're going to want to take a sample out of the side of the pipe. Frankly, it's just the best practice. So with a liquid, take it out of the side one way or another, whether you've got a probe or not. All right, so then within the facility, within the P&ID, the schematic of the system, where are we going to locate the sample tap? So when we're doing that, we need to have some sort of differential pressure to drive the flow through our sampling system. And there are a number of different places we can do that, of course. One of the most common ways to do it is to get a differential pressure across a control valve. Now, with a control valve, of course, it can be open or closed a certain percentage, and that's going to create a differential pressure. So that will be enough generally to allow push our flow through to our sampling system and then return it back to the process. With this, however, because that valve can vary in terms of the percentage in which it's open, with that scenario, we probably want to, there's some variability in terms of our sample delay time or our time delay. So as a result, our flow rate's going to change. We don't really know how long it's going to take to get the sample and transport it from the tap to the sample container. So that could be problematic depending on how much or little that valve is open. So that's one option, is to have it there across a control valve. And again, lots of people do it, but again, just understand that there's going to be some variability. So what's another option? Another option would be instead to put it across a pump. So we take it from the discharge side of a pump, and then we send it through our sampling system and then put it back to the suction side of the pump. Now with a pump, you're going to have a much more stable pressure differential, and so you're going to have a stable flow through our sampling system. So it's really going to help us to make sure that our, we have that consistent time delay, and we don't get into a situation where we inadvertently extend our time delay to an unacceptable level. Now, if we're not returning it to the process, which for a viscous liquid, we don't recommend, because for a viscous liquid, typically, again, if you dead end it into a system, it's going to cool down and then you could potentially plug it. So typically you will have a fast loop type of a system, but if you don't, make sure that you have that sampler located as close to the sample tap as possible, because it is going to be a dead leg, one long dead leg essentially. And then also make sure that you're probably going to want to heat trace that line as well, whether it's steam or electric, to keep that line nice and hot so that it doesn't plug. All right, so let's take a look at the design of one potential design of a high viscosity sampler, what that could potentially look like. So let's look at some of the key features. Typically, we are going to have that fast loop. So in this case, you got just a pipe, typically like a 1-inch or maybe 3/4-inch pipe that goes from left to right or right to left, either across the top of an enclosure or sometimes through the top of an enclosure. But pretty simple flow path for that fast loop. You're going to have some sort of a sample valve that allows us to divert some of that flow and send it down to our container. You're typically going to have an enclosure with a window. Most often it's going to be a stainless steel enclosure. It could be steel, could be painted steel, but generally that's not going to last too long. So we typically have a stainless steel enclosure, and very often you're going to have some sort of a purge on that enclosure as well to manage the vapors. It could be that you're actually suctioning that through with a venturi. That's a very common way of doing that, is with a suction pump like that. So that's the most common thing we see. Typically, you're not going to want to have a plastic window. You could, but again, remember the temperatures at which we're sampling. So if you get splatters, then you could melt the window, actually. If you've got a plastic window, if it's acrylic or polycarbonate, you could actually melt the window in spots. And you will get splatters on these windows. Normally, when you see the windows in these things, they're just filthy. Very difficult to see through. Most often, what we would recommend is to use a laminated safety glass. That way, you're protected against breakage, but at the same time, you have that temperature. You're able to withstand some of that temperature consideration as well. So generally, we're looking at glass for those things. Very often, you're going to have that enclosure mounted onto a pipe stand. That pipe stand, very common, of course, for grab sampling systems. Some sort of a shelf to hold the sample container. So in this case, our sampler is shown with again the metal paint can. What you typically want to have is either some sort of hole or grate that allows any drippage from the nozzle to go down through and go to a drain or something in the bottom. Very often you'll actually see these shelves made out of like an expanded metal grid or something like that, so that you don't have to worry about anything pooling on the on the shelf itself. So in this case, I actually show it with a hole in the bottom, and it actually the sample bottle nests in a location. That's another common feature, is a positive location for the bottle, or in this case, can, to sit in. That way you make sure that it's aligned to the nozzle. Right. You also have a drain, as I mentioned, to catch some of those, some of the drips, the overflow, the splatters, things of that nature. Shown here with 1-inch tubing, that would be the minimum. Very often you're going to want to see larger diameters just to avoid any sort of plugging that you have. Now, of course, as you get drips and whatever that goes down into that drain, they're going to solidify very often. So they're not going to drain too well by gravity unless you have that drain heated. So sometimes you will actually see that drain line heated, so that you can get that overflow or splatters to actually drain out of the system. Not uncommon at all. And then, of course, you need to have some sort of a nozzle to dispense the sample. So let's take a look at what options we have there in terms of nozzles to dispense. So Very common, of course, would be just a plain tube stub. If your temperature allows you to do so, basically you just have a sample coming in from the top, comes down through a tube stub down into the sample container. In this particular design, you also have the ability to vent out of a few different vent holes that surround that tube stub. So in this case, you could actually, again, hook up that Venturi fitting or whatever you're going to be using to draw that vacuum and suction those fumes out of there to your vent connection and draw that sample out. So that's a very common option if you can get away with it. But of course, as your sample is going down through that tube stub, it's going to cool. So how is that going to impact you? Is it going to cool enough by the time it exits that tube stub to where it could potentially start to solidify on the walls and plug things up? So another consideration, another option would be to use what's called a stinger. Now with the stinger, you again have a tube stub on the inside, but around that you have a steam jacket. So you would use a steam tracing around the outside. So you have a concentric tube around the outside of that tube stub, and then using that steam, you keep the whole thing hot right up until the tip. So if you've got a heavy viscous liquid that you need to keep hot right up until the point where you're dispensing it, using a stinger is a really good option. So then, of course, you could send your fluid down through. It flows nice and good because you are using that typically low or medium pressure steam to keep that nice and hot. All right, let's take a closer look at some of the options for a sample valve. With a sample valve, there are a number of different ways. The most simple would be to use just a simple angle pattern valve like what you see here. Angle pattern, of course, because we want our outlet pointed down towards our sample container and because we want to sample out of the side of our pipeline. So, this is a pretty simple way to do it. Very effective, cost-effective way to do it as well. Very often you're going to have some sort of steam trace on that line, on your fast loop line. So that's probably where our steam is going to be coming from for our stinger assembly. So it's very easy for us to hook up something like this, very easy and inexpensive. Now the downside, of course, is that we've got a pretty large dead leg on the inlet of that valve. So everything between the pipe and the valve seat is going to be a dead leg. So that could be potentially, a deal breaker for us in our sampling operation. Another drawback, of course, is that we can't actually purge this particular arrangement. So all of this, it's inside the valve. It's pretty difficult to get that viscous sample out of there. Now, you could potentially heat this valve, and that would help to keep that viscous liquid flowing. But even so, you're going to have some residue that's going to remain in the bonnet of that valve. And how do you get it out of there? Now, the ideal solution is one where you actually have a valve that's integral to some sort of a flow element. So you've actually flowing your fast loop through your valve body itself. Now, in this scenario, your valve seat can be much closer to the flow, so you're really minimizing that dead leg. You can actually also incorporate a second purge valve into the same arrangement. So let's take a look and see how that would work. So we would open up our sample valve, and we would have, again, just to set the stage, we've got that flow from our fast loop going in and out of the screen. You open up that sample valve to allow the sample to go down to the sample container and fill it up. And then when you're done, you can go ahead and close that valve. You're going to still have some residue inside that sample valve, but you can then open up your purge valve. And again, this is typically going to be steam. And then that purge can actually go through the bonnet of our sample valve and then down through our stinger or through our nozzle and clean everything out. So that's a really effective way of taking a sample, taking a viscous sample, and then cleaning out the system after the fact. Now, the drawback, of course, is that these things are not typically readily available. So this is a make-to-order type of a product, maybe even a custom product for a lot of manufacturers. So this sort of thing could potentially have a longer lead time and then a higher cost. So, ideal solution from a purely technical standpoint, maybe not from a commercial standpoint. So what would be a compromise solution? A compromise solution could be a combination of the two. So here we've actually utilized a cross pattern valve Here you can see that circled there. With a cross pattern valve, you've actually got one inlet but two outlets. And what that does is we can actually use that second outlet to couple a purge valve to that. So here we have that cross pattern valve. We got a similar valve with but an angle pattern where we can introduce steam as a purge fluid. And now we've got the same basic functionality as our ideal integral valve solution. Now, we do still have a little bit of a dead leg, of course, on the inlet, but it's not as big as the one that we had initially with that different valve series. So this is relatively easy and inexpensive to implement. These components are generally available, so this could be a good compromise solution for a viscous sampling operation. Now, another approach when we're sampling, another sample valve option is to use a piston valve. Now, with a piston valve, these are generally pretty well suited for sampling viscous liquids, slurries, powders, things of that nature. Very commonly used for a simple sampling operation, and they're typically mounted directly to the pipeline. What's really nice about this is that with the piston, it actually pushes any residue back into the pipeline when we're done sampling. So it's nice that in that it stays relatively clean. There are some drawbacks, but it does stay relatively clean. And then there are options for metal seated versions of these, so we can generally take the temperatures that we're talking about when we're looking at high temperature, high viscous flows. So at this point, we're actually going to show a short little video to show how this valve actually works.
Here we can see an image of a piston valve and how it works. In this case, it's showing it actually sampling a powder, but in reality, it can also be used for viscous liquids. You rotate the handle to draw the piston back, and that allows the viscous liquid or powder to flow into the bottle. You can adjust the flow rate by opening or closing that handle more or less. Then, when you're done sampling, you can rotate the handle to push the piston back forward, which in turn pushes any material from the inlet of the valve back into the pipe.
Okay. So now we've seen how a piston valve works. What are some of the limitations? So one of the limitations is that you typically don't have a probe with this valve. So as I mentioned, it's very often attached directly to the process pipe, and very often it's going to be attached to a pipe nozzle like what you see there. So as a result, because you have the the volume of that pipe nozzle, which can act as a dead leg, and then also because you're sampling essentially from the wall of a pipeline, the representativeness of when you're using one of these can be somewhat questionable. There's also generally no protection for the operator. If you remember the picture from the previous screen, you've got a bottle or a can that's exposed, typically not feeding into an enclosure or something like that. You do have potential cold spots in this valve. You can actually buy steam jackets for them to fit around them to keep them nice and hot, but that's an added expense. Typically, the valves are unable to be purged. And while generally they're pretty good about pushing the fluid back into the system after you're done, there is actually some entrapment areas in there. So, for example, here we show a valve in the open position where all the red areas are what's wetted, and then when you go ahead and close that valve, push it back, some of that, a good portion of it is going to be pushed back into the process, but at the same time, you will have some areas that just don't get scraped off, don't get pushed back in. So that's contamination that could impact our next sample. So there are some entrapment areas there to be concerned about. And as I mentioned, purging these things can be difficult or impossible depending on the valve model that you're working with. Now, one thing that you will sometimes see with a piston valve is converting that to a fixed volume sampler. This is a nice thing when we are talking about dispensing a high viscous, high temperature sample, because it enables us to pre-measure out a certain amount of liquid, and then we don't have to worry about overfilling our bottle. So we use just a small chamber or a sample cylinder that's attached to the valve to actually fill that up first, and then we use a purge gas or something to push that into our sample bottle. So This is a pretty nice way to do it, and it really is pretty effective generally. But there are some drawbacks with this particular approach. For example, with this little sample cylinder or little sample chamber that we have, you sometimes, what you end up with is that there's no way for the gas to escape out of that little sample cylinder. So as you're filling it, it's filling up to a point where you have the process pressure is balanced against the gas pressure. And so depending on your process pressure, the amount of liquid volume that you get in that sample container is going, sorry, that you get into that little sample cylinder is going to vary. And note that it is at your process pressure. So if you've got a high process pressure, then that is the pressure at which you're going to be dispensing your sample into the container. So there are some drawbacks, but let's take a look at how that actually works. We've got a short little video that shows us how that actually works.
Here you can see the sampling apparatus. Note that below the piston valve you have a small chamber. As we open the piston valve, that chamber fills up with liquid, enabling us to pre-measure out a certain amount of liquid. After the chamber is full, we can close the piston valve and turn on our purge gas. The purge gas will then transfer the sample from the chamber into our sample bottle. Once the sample bottle is full, we can go ahead and close the valve, take our bottle out, and take it off to the lab.
So with that, again, there are some challenges with that, but there is an alternative design that enables us to overcome some of those challenges. The same benefits. We're still preventing overfilling. We're filling up our bottle to what's typically a 60 to 80% fill. But what's nice about this particular system is that it actually isolates you from the process pressure, high process pressure, and dispenses the sample at the pressure of the purge fluid. And also, it enables you to have a nice consistent fill volume because of the way it's designed. Now, it is a bit more complex flow path, so it could be, you're typically going to have to heat this in order to keep everything flowing through there, but it is an option. Let's see how this actually works. So here we can see we've got two valves. We've got some ball valves that are geared together, and that enables flow to go through a little fixed volume cylinder that's on the panel. So when I switch my valve handle to the flush position, it switches those ball valves and allows the flow to go through that container and actually fill that up. And because we're filling from the bottom up and we're going back to the process, any air that was in that cylinder gets completely removed. And as a result, we've got a very consistent sample size. Now, once that little cylinder is full, we can go ahead and switch to the sample position. And then we're actually using the purge gas, in this case, nitrogen, to push that liquid out of the little sample container, the little sample bottle, and into the sample container down below. So this is a nice, effective way of doing it. As I mentioned, you do actually have to keep this hot because you need to keep things flowing. So here's an example of how that was actually done. This was actually done by our sales and service center in Dusseldorf. So they actually combined some of the Swagelok products to create a pneumatically actuated version of this panel where it's inside of an enclosure. You can see that tubing zigging and zagging back and forth. That's actually a steam trace for the enclosure to keep everything hot. So this would be a heated and insulated enclosure. You can actually heat trace those lines going through there, but on some of these panels, the small diameter lines, it's pretty difficult sometimes to actually heat trace a line with steam, a small diameter line with steam. So sometimes it's more effective to just heat the entire enclosure. That way it's in a completely heated environment. You've got a nice thermal soak for the entire thing and you don't have any cold spots. Now, typically you're going to be dispensing that into a sample container that is housed in a separate enclosure, because then you don't want to be opening that door to let all the heat out. So that would be inside of a separate enclosure. So this is one way that you could potentially do that and make it a nice safe operation to keep the operator isolated, but at the same time make sure that they can't accidentally overflow that sample container. So this is a nice way to do that. Another nice feature done by our same sales and service center in Dusseldorf, really done some innovative things with our sampling systems is they've actually developed a no bottle, no flow system. So that means if there's no bottle in place, then actually it won't allow any flow to go through the sampling system. And the way they did that is with a mechanical interlock. The bottle has to be in place in order to allow those ball valves to turn. So that's a really nice feature that we can add to these types of systems to make sure that you're not, again, dispensing a high viscous, high temperature sample into a sample enclosure where there is no bottle or no paint can in place. So that is a really nice option. Now, the way our sales and service center was able to do this is that Swagelok actually has a pretty broad range of standard sampling systems. Most of them aren't really geared towards high viscous liquids, but through some training programs that we have for our sales and service centers, we really enable them to customize these things. So we actually call these not a product line, but rather a design platform. Now, with this, we're using the knowledge that we've provided to our sales and service centers to create these high viscous, high temperature sampling systems, and really, limitless customization that we can do through our sales and service center. So, and we're doing that at the local level. So, really good support for you guys if you need it. Well, that's all the content I had. If you've got any further questions, there's a lot of different options for you. We, of course, Swagelok has a lot of good presence on social media, be it LinkedIn, Facebook, etc. We also have, YouTube channels, and we've also got a blog on our website called Reference Point, specifically for sampling systems. So those are all options for you to get additional information. And at this point, we're going to go ahead and address any questions that you might have.
All right. Thank you very much, Matt. A few of you have already submitted questions, so we're going to jump right in. As a reminder, if you would like to submit a question, type your question into the question window on the side of your screen and hit the submit button. So let's see. One of the listeners is asking, can this sampling process be automated by, for instance, pacing the samples either by time or flow, making them time or flow proportional?
Yeah, absolutely. If you're monitoring the flow, you can absolutely do some automation around that. I showed you that pneumatically actuated version of that we were using to create a fixed volume sampler. Imagine if you were going to do that and periodically take a sample. Maybe you've got multiple sample containers lined up, and you could take multiple samples. Do that on a flow basis, so that you end up with a representative sample across a certain amount of time. So, definitely options there in terms of automation, working, PLCs into this, and or maybe even just controlling it with your plant DCS. So, lots of different options there for automation. But yes, absolutely, there are opportunities to automate that. And frankly, that's one of the strategies we have for safety, is to take the human element out of it. If we can automate these things and make them more robust and make them less likely to have that human interaction, then the better off we're going to be.
Sure. Yeah. Can you cool the sample to make it safer to handle as well?
Yeah, you can. In some cases, you're going to be cooling it just a little bit, and it's still going to be pretty high temperature. As I mentioned with like the bitumen, you're not going to get that down to the 160 degrees, or rather 140 degrees Fahrenheit, that would be considered a safe handling temperature. But you're probably going to cool that down from 700s to say 400 or 500. Now, ironically, you might actually be using steam as the cooling fluid to do that. In many cases, cooling water might actually cool the sample too much. Again, steam is often used as a cooling fluid in these applications. And depending on the viscosity of the sample and the nature of it, you could potentially cool it down using cooling water down to some safe handling temperature. But again, understanding what that relationship is between temperature and viscosity, you might or might not want to do that. So just understand your fluid before you go down that road.
Sure. When you use a purge, where does the purge fluid go?
Okay, yeah. So when you're sampling into that enclosure, and now you've got you've got a purge fluid going in, be it nitrogen or be it steam. Where is that going to go? I did mention a venturi is one potential option for sucking away the vapors. You could just have some other sort of a vent system that would carry away those vapors and the purge fluid. It could actually be that the purge fluid just goes down the drain connection as well. That's another potential option as well. So seeing a lot of different configurations out there. Just depends on what utilities you have on sites and what's what the site standards are.
Sure. Can you use one panel to sample from multiple or different locations?
You can. With grab sampling, we generally say that it's not worth it. With an online analyzer that's out in the field, you'll often see some stream switching operations where you have one analyzer that's analyzing multiple streams. But that's a pretty expensive instrument and a pretty expensive installation, so it makes sense to minimize the number of those installations. With a grab sampling operation, they're generally inexpensive enough to where you're typically going to want to have dedicated sampler for each sample point. It's just going to make life a lot easier. You're not going to have to worry about plugging in plugging up with the stream switching operation. You're not going to worry about transporting the samples over long distances. So in general, you're not going to worry. You're not going to want to do that typically.
Okay. One of the listeners is asking, how do you actually measure the viscosity of highly viscous fluids?
That's a good question. I honestly don't know. I think there are meters that can measure that. I don't have any experience myself in measuring that, to be perfectly transparent. So I don't know the answer to that one.
All right.
Yeah.
Let me, this might be a good one to start wrapping things up with. Somebody says that in our case, we have a very viscous petroleum, and the viscosity is highly dependent on the temperature, and it is produced with gas and solution.
Mm-hmm.
Which method is recommended for sampling at reservoir temperatures of 130 degrees Fahrenheit and keeping the gas in solution, 250 psi, the pressure number supplied?
Right. Yeah, sure. So in that scenario, if you've got a gas dissolved into the liquid, and if you need to keep it under pressure in order to keep it from vaporizing, then you really don't have much of a choice other than to use a sample cylinder. So in that case, you're going to want to use a sample cylinder that has relatively large end connections. It has valves that are probably going to be ball valves instead of a globe pattern valve on either end, just to minimize the number of flow restrictions going through. For quick disconnects, that you have in that scenario, you might even have non-valved quick disconnect fittings on there. So again, to minimize the flow disruptions and to keep everything flowing through the sample cylinder. But if you've got to keep your sample under pressure, then a sample cylinder is going to be the way that you have to go in that scenario, because a bottle or a paint can, those are just not going to do it. Those are really operating at ambient ambient pressures. Now, maintaining a temperature while you're transporting that sample, that's pretty challenging to do. You can put the sample cylinder in some sort of an insulated case. We've seen that done. We've seen attempts at actually having a where you actually have a heated sample case. But of course, you have to have a power supply in order to do that. So you're in some sort of a vehicle at that point that's where you're using the power from the vehicle to keep that sample container or case, if you will, hot. So there are options out there, but that gets to be logistically challenging for sure.
Sure. Excellent. Well, thanks very much, Matt. I'm afraid we've run out of time for today. For those questions we didn't have time to answer, we'll be getting back to you by email. That concludes today's presentation. On behalf of Oil and Gas Journal, I'd like to thank Matt for his presentation today, Swagelok for sponsoring today's webinar, and of course, all of you for joining. Have a great rest of the day.